so far we have looked at different aspects of the physical infrastructure around a microcontroller, right? For example, GPIOs and communication protocol, UARTs, right? But one very important aspect of this is to also take a look at some details and to say, okay, how do I even know what a microcontroller has, right? And this information is usually provided by means of what are called data sheets, which basically their entire purpose is to sort of describe an electronic component in sufficient detail that you can do something useful with it, right? So what is important in terms of data sheets is, of course, to know what they are. They basically describe electronic components, but more importantly you need to know what to look for and where. So what I am going to do is to very briefly look at examples of a couple of data sheets. One of them is for the STM32 microcontroller, the C031 family that is being used in the examples that we are looking at, and another one is basically for a standard red LED, right? And this is from the Farnell web page, Farnell being a sort of reseller of electronic components, right? So they have a data sheet corresponding to one of the LEDs that's available in their inventory, and we are going to take a look at what we can infer from that. So what we have over here is actually a data brief. It's not quite a data sheet, right? And this is for the STM32 Nucleo 64 boards, right? And if you look at it, basically what's the difference between a data brief and a data sheet? A data brief is more meant, it's not exactly a marketing document, but it is meant more for getting a high level picture of what a particular part or a component or something is going to do, without necessarily going into a lot of detail about how it does it. In this particular case for the STM32 Nucleo boards, what it tells you is, for example, gives you information about the different families that are present in here, the Nucleo C031 C6, Nucleo F series, Nucleo G series, L series and so on, right? And in particular, if you look at it, it also in this case has hyperlinks that give you more information about each and every one of these if you were to click on them, but that's not our purpose right now, right? It gives you some information about common features. It tells you, for example, that all of these boards use an STM32 microcontroller in an LQFP 64 or 48 package. What is LQFP? It refers to the type of package or the chip package that is used, right? Not relevant for the end user, but very relevant for a system designer, because this is the kind of part that you choose, and the design of your PCB depends on the package that you choose. It also tells you a bit more about the boards. For example, there is one user LED that is similar to the Arduino kind of system. It has two push buttons, one is a user push button and one is for resetting the entire system. It uses a crystal oscillator. This is how it provides a clock to the system at 32.768 kilohertz. Why this particular number? Because it's actually 2 to the power of 15, which means that it can very easily be divided down to get like a 1 hertz signal, right? So it turns out that because of that, people sort of chose this as a nice reference, and it's common enough that you find it in other places. But does that mean the system works at 32 kilohertz? No. There are other ways by which the internal clocking can be made much faster, right? So I'm not going to go through each and every one of these. What is important is it sort of gives you a list of common features and also tells you something about what is specific to some of the boards. In particular, you can find that there are some of the boards that provide you with USB connectivity, some of which have cryptography primitives built into them, so they can actually do high speed cryptography, encryption, decryption and so on. The different kinds of connectors that are available on the boards, the debugging capabilities, and then of course it gives you a little bit more actual description of the boards themselves. After that, it goes into information about ordering, right? How you can order, what are the different variants in which it can be ordered, the marking, which basically talks about the variants, the product codes, product identification and so on, right? Again, not really important unless you are getting to the point of designing a system, but you should be able to look at a board and at least read some of this documentation and understand what it refers to, right? including things like the codification, what is the MCU series, the product line, the package pin count and so on. All of this is useful to know because at the end of the day it impacts what you can do with a particular microcontroller. The development environment, the system requirements, these are actually a bit more to do with the specific tool chains that are provided as part of from ST Microelectronics, and what demonstration software is there, and finally the document revision history, which actually tells you what were the changes made to the document itself. Pretty much all data briefs and data sheets will have some kind of standard structure like this. Okay. Alright, so this was with regard to the data brief for the Nucleo boards. On the other hand, the data sheet corresponding to something like the actual STM32C031 over here, right? This refers to the specific microcontroller, not the board. It refers to just the chip alone. And here it's actually a bit easier to see the different variants, right? You can see the kind of packages it's available in. One of them is called a TSSOP, another one is the LQFP, that's the low quad flat package. Then there is the UFQFP, which if you look carefully at it, you will see that the pins over here are actually literally almost under the package. These two are, and in fact all of these are meant for what are called surface mount kind of technology for the PCB design, which is the most common form for any non-trivial, not non-trivial, but for any even slightly complex form of PCB, especially involving microcontrollers and so on. Through-hole components are very rarely used in PCBs. They can only really function at fairly low speeds compared to what you need, and it's relatively rare to find through-hole type of microcontrollers, except for things that are specifically targeted to run at low speeds, in which case they might even be available in packages that can directly fit on breadboards. It's not unheard of. In fact, the Atmega series, for example, has things that can directly be plugged into breadboards, and that's perfectly usable. But whenever, in terms of the use cases where you are designing a board and you want to have more functionality, the most common forms are some kind of surface mount devices. So this sort of tells you about the different kinds of packages that are available. But the very first line out here is itself very informative, right? It tells you that the STM32C0 series has an ARM Cortex M0 Plus type of MCU. It's a 32-bit MCU, which basically means, refers to the size of the registers internally. It has 32 kilobytes of flash memory, which can be used for storing the program as well as configuration information, and 12 kilobytes of RAM. Interestingly, you can have a larger program and a smaller amount of RAM. The RAM is used for the actual running of the system, right? All the variables, the temporary storage, the program needs to get loaded into RAM and then run from there. So the RAM is what finally determines what can run at the actual execution time. The flash can be used for storing additional information, the configuration, the actual program or parts of it, which get loaded as and when necessary. It also tells you that it has two USARTs, Universal Synchronous Asynchronous Receiver Transmitters. Of course, we have primarily been talking about using them as UARTs, but this is sort of a superset of the same. It has timers, which we will encounter later when we look at how they can be used for automatically triggering events that need to be responded to. An ADC, analog to digital converter. Communication interfaces. Now, what are these communication interfaces? You'll have to look through the data sheet to find out. And finally, it also says 2 to 3.6 volts. Those are the usual operating range of voltages for this, right? And of course, the features. So the first page of a data sheet typically has a summary of the features, right? It basically talks about the core. It tells you about the minimum and maximum operating temperatures, the different kinds of memories, various kinds of features that it has, clock management, how it can work with different kinds of crystal oscillators and other kinds of oscillators as well. It also turns out to have an internal oscillator, right, which you can use if you don't, for example, want to provide a separate external crystal to reduce the number of parts on your PCB. But as you can see, this clock is not very accurate. It only gives you a tolerance of 1% or in some cases up to 5%, what that means is your frequency could be off by 1 to 5% from what you expect, right. In other words, not good for very accurate timing. If you were to run, let's say, a watch using this and use the 32 kilohertz RC oscillator in order to count seconds, you would basically be off by maybe 1 or 2 seconds every minute, right, and you would rapidly lose time. So it's not really meant for that kind of application, whereas crystal oscillators can be very finely tuned. Up to 45 fast IOs, what that means is, depending on the type of package that you have over here, you could have a different number of GPIOs, right. And interestingly, so this basically says they are all 5 volt tolerant. So you remember we had the discussion about what happens if I connect a 5 volt sensor when my CPU is running at 1.8 volts or so. In this case, the CPU is not running at 1.8, it would be at something higher than that, 2 to 3 volts at least. And what it says is that because of that, if you were to directly take an external peripheral which is generating a 5 volt signal and connect it here, you are fine. Your CPU is not going to get damaged. It is tolerant of 5 volts. There is DMA, which we will talk about later. There is also A to D converters, which can have up to 19 channels for conversion, right. There are timers, there is a RTC, what's called the real time clock, right, and the communication interfaces, right, this COM-IFs that was written up here. More details about it, it basically says one I2C bus. All of these we will look at later in terms of understanding what these buses are. 2 USARTs and one SPI, which can go up to 24 megabits per second, right. It has debugging support, and well, these are more to do with the packaging itself, and they are more standards in terms of compliance, in terms of safety and disposability and life cycle management of the actual physical parts. So this was the one-page summary of the data sheet, but then it starts going into a lot of detail, as you can see here, right. It gives you a functional overview, it talks about how the peripherals are connected, it gives you information about the real-time clock, it describes the pins and the electrical characteristics, which includes things like how much is the minimum voltage, the maximum voltage, how much current will be drawn by it, what are the different sort of power management modes that can be available, and finally also the different packages in which you can buy this, right. So there is a lot of information in the data sheet. As you can see, the introduction basically tells you a little bit more about the functioning of the thing, but for example, things like memory mapping and the control registers are not covered in the data sheet, right. For that you need to go and look at the reference manual, but this tells you exactly where to look. So you need to look for this particular reference manual, and in that, for this Cortex series, it will give you information about how the memory map is constructed, which address is to be used for speaking with which register, and which are the control registers that are available in the system. Okay. And once you have that, there is also more information about the different variants of the family, right, each of which has some differences, the amount of flash memory, or maybe the number of GPIOs, the number of ADC channels. Those might be the differentiating parameters in each of these configurations, right. So there is also a complete block diagram which is worth looking at, because basically what it shows you is that the CPU by itself is actually a small part of your entire system. What you do have after that is voltage regulators, the internal clocks, the reset and clock control, the GPIO ports over here, the A to D converter, SPI, and this entire bus out here which communicates with the timers, the USARTs, the I2C interface, and so on. Okay. So knowing how to read this data sheet plays an important role in how you can make use of it, and the kinds of things that you can infer from the kind of uses to which you can put this. For example, if you need to get a microcontroller with a large number of ADC channels because it needs to collect data from many different sensors, or if you need something more than 2 USARTs, or if you need multiple SPI communication capabilities in order to control other kinds of peripherals, right, or The timers, as we will see, can be used for things like pulse width modulation, which means that you can actually use it in order to control the drive for motors and things like that. Different families over here have different capabilities in those terms. This is of course the Cortex M0 series. If you look at the ESP series of microcontrollers, there will be similar data sheets that describe their capabilities. If you look at the MSP 430 from Texas Instruments, they will have their own data sheets. PIC, Atmel, each of them will have their own data sheets. Many of them will be similar in some aspects, but almost certainly each one will have its own differentiating factors. So knowing what to look for and identifying which are the ones that actually matter to you in terms of your design will be something important in terms of how you build a system or how you use a pre-existing system. So this is one other example of a data sheet. As I said, this is from the Farnell website, but it basically corresponds to the data sheet for a standard LED, which is the red emitting color, which is made by a company called Multicomp, right? And it sort of gives you very brief features, but it's an LED, it has only so many features, it's not a very complicated data sheet, right? It tells you things including the physical package dimensions, right? And the tolerances of each of these, meaning, okay, it's supposed to be 5 mm, but it might be off by up to 0.2 mm or so, right? So that's basically what it's indicating out here. Rather, 5 mm, that's this is also in inches, millimeters and inches. So this is not really talking about tolerances. What this is giving you actually is that these are the sort of nominal values, and there is something else which sort of talks about the minimum values that you could potentially see over here, right? And yeah, the tolerances are 0.25 mm unless otherwise noted, meaning that all of these things, when it says something like 5 mm over here, it could be 5 plus or minus 0.25 mm. Physical, real life, right, is not like a program where everything is just either a 0 or a 1. You have tolerances, you have some kind of inaccuracies in your measurements, and this needs to indicate that, because when you are actually designing your mechanical board, you need to be aware of the fact that something which says 5 mm may not be exactly 5 mm, it could be up to 5.25 mm in this case. Okay. But what's more important or interesting from our point of view is this second part, which talks about the maximum ratings, right? It says, for example, that the power dissipation maximum is 80 milliwatts, right? So where does that come from, right? We'll have to look at where is the power dissipation inside the LED going to come from. One of the things over there is what's called the peak forward current, and it says that the maximum current that it can take without getting damaged is 100 milliamps. But that should only happen at a 1/10 duty cycle. In other words, if I continuously try pumping 100 milliamps through this, right, for more than 0.1 milliseconds, I could potentially damage my device. But if I have 100 milliamps for about 0.1 milliseconds and then for at least 9 times that long, in other words for about 1 millisecond after that, I don't pump 100 milliamps through it, and then once again I have a short burst of 0.1 milliseconds of 100 milliamps, that should be okay, my LED will still survive. That's basically what this piece of information is telling you. On the other hand, the continuous forward current can be 20 milliamps, that's what it's rated for, and in fact when you are doing your current limiting calculations, this is the number that you should ideally use, right? Use 20 milliamps because it says this is the current it can safely tolerate in a forward direction. It also says that the reverse voltage is 5 volts. What that means is that if you accidentally or intentionally connect the voltages in the wrong direction, right, you switch the anode and cathode of the diode and connect them the wrong way, and you put effectively what's a minus 5 volts across it, anything worse than that is going to damage the diode, right? And the derating essentially says that once you go above 50 degrees centigrade, the current that you are allowed to sort of pump through it sort of decreases. You shouldn't be trying to send too much current, because as it is the system has got hot, the behavior of the semiconductors also changes slightly at higher temperatures, and trying to send too much current through it is most likely going to damage it. The operating temperature range is specified. All of this once again is for system designers, but if you happen to find yourself in Antarctica and wonder why your microcontroller is not working, be aware that there are limits on where the how much temperature your system can tolerate. And of course, the other interesting thing about this particular data sheet is it also gives you the actual diode characteristic, right, which basically tells you why this, the 20 milliamps at around 2.2 volts of forward voltage is what it is sort of nominally expected to operate at. As you go to 2.4, 2.6, you have gone above 50 milliamps, and that's most likely going to start damaging your system, right. It also tells you about the wavelength characteristic, which tells you why it is basically red in color, right. You have a nice thing between 600 to 650 nanometers, which is in the red range of the visible spectrum. It also gives you more information about the intensity and so on, which I am going to skip over, but you can look at if you are interested, right. So the bottom line is these kind of data sheets provide a lot of useful information, not just for the system designer, but also the system end user, right, in order to know what the capabilities of your system actually are. And knowing how to read the data sheets is very important from a practical point of view.